This is Unit 2, Topic J. We're going to be talking about the derivatives of logarithm functions. We'll specifically talk about the natural log, and then we'll look at a slight adaptation for the log of any base. But let's start by thinking about what is the derivative of the function y equals the natural log of x. Okay, we'd like to find dy dx. Because we don't know the derivative at this point, we're going to adopt a method that's going to turn this into an implicit function whose derivative I do know, and we'll use that to discover the derivative of ln x. So since I don't know this yet, I'm going to start by just exponentiating. I'm going to say e to the y power equals e to the ln x power. So I've done the same thing to both sides, right? Just raised both sides on a base of e. That means e to the y equals e and ln are inverse functions, so that right-hand side just simplifies to x. Now my function is now implicit, but the advantage is I know how to take the derivative of both of those sides. So the derivative of e to the y is still e to the y times by the chain rule dy dx equals the derivative of x with respect to x is just 1. So dy dx is 1 over e to the y. But e to the y is the same as x, right? So I could just replace that e to the y with an x. And I have the unusual situation where I did a derivative implicitly, but I got an answer that just contains x's, which is great. So our conclusion is that the derivative of the natural log of x is 1 over x. So down here, let's fill that in the little chart. If f of x is ln x, then f prime of x is 1 over x. All right, let's also address the log of another base. Y is equal to the log base b of x. I'm going to start by using the change of base formula to rewrite this. Log base b of x can also be written as the natural log of x divided by the natural log of b, or 1 over the natural log of b times the natural log of x. Notice this is just a constant, right? So if I want to find the derivative, dy dx, I'm going to keep my constant multiplier the same, 1 over the natural log of b, and just multiply it by the derivative of ln x, which we just figured out was 1 over x. So I end up with 1 over x times the natural log of b. So if I want to take the derivative of a log function, base b, that derivative is 1 over x ln b. So 2 new derivatives for us to work with in this section. I'll be primarily concentrating on the natural log. The only difference with any other base is just that extra little factor of ln b in the denominator. So some examples. I would like the derivative first of x squared times the natural log of 6x. Back to our product rules again. F would be x squared, and g would be the natural log of 6x. So f prime is 2x. And for g prime, I'm going to have to use a chain rule. First of all, we said that the derivative of the natural log function for ln x was 1 over x. So for ln 6x, it's going to be 1 over 6x. Notice that the entire argument of the natural log function ended up in the denominator. Then I'm going to multiply using the chain rule by the derivative of the inner function, which is 6. And I actually just end up with 1 over x again once those 6's cancel out. So, dy dx. Fg prime, x squared times 1 over x, plus gf prime, 2x times ln 6x, and I can let one of those x's divide out, and I get x plus 2x natural log 6x. All right, example 2. Definitely a chain rule here. I'm going to say that my outer function is that 6th power. So I'll start with a power rule. 6 times all of this, ln x plus 3x to the 5th power. And then times for the chain rule, the derivative of what's in the parentheses. So the derivative of ln x would be 1 over x, plus the derivative of 3x is 3. And there's really not much I can do with that. If you wanted to, I guess you could distribute the 6 into the parentheses, but it doesn't really gain anything, so I'm going to leave it factored out. All right, number 3. We are looking at a quotient rule on this one. So f would be our numerator, ln x minus x squared, and g the denominator, e to the x plus 5. That means f prime is 1 over x minus 2x, and g prime is e to the x plus 0. We haven't used a quotient rule for a little bit here, so let me remind you that it's gf prime minus fg prime over g squared. So dy dx is equal to gf prime e to the x plus 5 times 1 over x minus 2x, subtract fg prime, ln x minus x squared times e to the x over g squared, e to the x plus 5 squared. All right, we've got kind of that factor, but subtraction between, so it's not a completely multiplied out or a completely factored form. So I'm going to go ahead and multiply out my numerator. Just multiplying those two binomials will give me 1 over x e to the x minus 2x e to the x plus 5 over x minus 10x. And then I'm going to distribute both the negative and the e to the x here. So minus e to the x ln x plus x squared e to the x over e to the x plus 5 squared. And this is just going to be one that isn't going to look very nice. The only thing I don't like about this right now is I don't like the complex fraction. So let's clear the complex fraction. I'm going to multiply top and bottom by x. And let's see, those x's will cancel out, so I'll just get e to the x minus 2x squared e to the x. X's cancel again, so plus 5 minus 10x squared minus x e to the x ln x plus x cubed e to the x over x e to the x plus 5 squared. And I just have to accept that this one's not going to get any better than that. So there in all its glory is that derivative. All right. One of the things that we want to also talk about is the fact that using the natural log is actually sometimes an advantage to us when we're taking derivatives. Here's what I mean by that. You all know that there are particularly some properties of logarithms, right? And those properties can be used to make derivatives easier to do. They can help us to actually avoid product and quotient rules, in fact. Let's take a look at a few other log examples, and I'm going to particularly call your attention to a couple of the log properties we're going to use here in order to make our derivatives easier to do. Typically, the expanded form of a log is an advantage when you're doing a derivative. So in part number 4 here, I've got the natural log of x to the 4th. I certainly could do that derivative just the way it's written. In fact, you know what? Let's do it once that way. I've got the natural log of x to the 4th. So I'm going to start by taking 1 over x to the 4th. Again, notice that what was inside that log, that x to the 4th, ends up inside my denominator, x to the 4th. And then I would have a chain rule times 4x cubed. So I end up with a 4 on the top, and then I could divide out those x's and just a x to the 1st on the bottom. Right? So that would be the chain rule method. Or I could also use a log property before I ever start the derivative. Let's go back to f of x equals the natural log of x to the 4th again. One of the log properties says that an exponent can be brought down in front of the log. So I'm not doing a derivative yet. I'm just using that log property and rewriting this as 4 ln x. That's just a property of logarithms. In fact, if your log properties are a little bit rusty, I'll just call your attention to the fact that on your list of formulas, the same page as the trig identities has the log and exponent rules. And I just use that one, right? It says the log of x to the y power is y times the log of x. I just use that for my natural log function. Well, if I now take the derivative, 4 is a constant multiplier, and then the derivative of ln x is 1 over x. And so I get 4 over x. Again, and notice that this did not require the chain rule. So using that log property meant I didn't have to do as complicated a derivative. Let's try that again. In number 5, we've got the natural log of the square root of 2x plus 6. We're already used to the fact that usually when we have radicals, we like to change them to fractional exponents. They work a lot better for derivatives. Now I'm going to use that property of logs again. I'm going to say that's the same as 1/2 times the natural log of 2x plus 6. Notice I haven't done any calculus yet, no derivatives. All I've done is use that property of logs. This is now a simpler form, and so when I do go to do my dy dx, the 1/2 is a constant multiplier. I don't have to change that. And then I take the derivative of the natural log of 2x plus 6. So notice I've got 2x plus 6 inside my log. That means the derivative is 1 over 2x plus 6. Whatever's in the log goes in the denominator. And then times for the chain rule, the derivative of that inner function would be 2. I can divide out those 2's. So I just end up with 1 over 2x plus 6. All right. In number 6, we have another example where using the properties of logs first is going to be really helpful. I've clearly got a quotient here, but one of my rules of logarithms is that the log of x divided by y is the log of x minus the log of y. Much easier to take the derivative of subtraction problems than division, right? So let's use that log rule. I'm going to rewrite this as the natural log of the top, e to the x, minus the natural log of the bottom, x squared plus 9. Again, this is just algebra, just log rules. Haven't done any derivatives yet. A little bit more algebra here. Again, ln and e are inverse functions. So that's going to just simplify to x minus the natural log of x squared plus 9. All right, that's about as simple as I can get that algebraically. So now I'm going to go ahead and do my derivative. Derivative of x would be 1 minus, and same deal here, whatever is inside the log function goes in the denominator when I take the derivative. So 1 over x squared plus 9 times my chain rule here. The derivative of that inner function would be 2x. So I have 1 minus 2x over x squared plus 9. All right, let's take a look at number 7. Number 7, we have an implicit derivative. And inside that natural log function, there's a product. Once again, we've seen before product rules. We can do them, but they're a little bit of a pain. But in my rules for logarithms, it says the logarithm of a product is the sum of the two logs. So once again, it's going to be worth my time to do a little bit of algebra first. Let's split this up. Let's write this as the natural log of x plus the natural log of y. Notice no more product rule. Plus 5x equals 30. Now that it's algebraically a little bit simpler, I'll go ahead and do my implicit derivative. Derivative of ln x is 1 over x, plus the derivative of ln y would be 1 over y, chain rule, times dy dx, plus the derivative of 5x is 5, equals the derivative of 30 would be 0. So I've got 1 over y dy dx, and I'll take everything else to the other side, equals negative 5 minus 1 over x, and dy dx is negative 5 minus 1 over x divided by 1 over y. Now I don't love the complex fraction, so let's get rid of it. Let's just say instead of dividing by 1 over y, I could multiply by y over 1. And so my simplified form for the derivative would be negative 5y minus y over x. All right, well that works out so well that sometimes we say, gosh, even if I don't have these natural logs to help me, it would sure be nice to be able to use the log properties. So sometimes we can introduce the natural log into a function before we take the derivative. That allows us to take advantage of these log properties that have worked out so well for us. This is a process called logarithmic differentiation. And it's especially useful when I have a really complicated function like this. Notice this would have a product rule on the top, a product rule on the bottom, a quotient rule over all, and multiple chain rules in the middle. This function's a mess. So what I'm going to do is, using the process of logarithmic differentiation, I'm going to choose to take the natural log on both sides before I start. So I'll get the natural log of y equals the natural log of this great big mess. I'm going to go ahead and rewrite this as x cubed minus 2 to the 1/2 power as I rewrite. And now, again, still algebra, let's just take advantage of all those log properties and break apart that great big mess on the right-hand side. I would have the natural log of e to the x plus the natural log of cosine 6x, right? The product became a sum, minus, because this is in the denominator, I'll bring this 1/2 down, so 1/2 times the natural log of x cubed minus 2, and this is still in the denominator, so minus the natural log of sine x. Okay. So I had 1, 2, 3, 4 factors inside that big fraction. They're now 4 separate terms, making the derivative much easier to do. Before I actually take the derivative, let's just remind ourselves the natural log of e to the x is really just x. So I'll do that little bit of algebra, and now I'm ready to finally take the derivative. Now this is an implicit derivative, notice. The derivative of ln y would be 1 over y times dy dx for the chain rule, but it's not going to be hard to solve for dy dx, right? Just multiply by y when I'm done. And on the right, I get 1 plus everything that's inside the natural log goes in this denominator, so 1 over cosine 6x. Chain rule, the derivative of cosine x would be sine, and actually it's 6x. And one more chain rule, the derivative of 6x would be 6. So there was still a double chain rule there, even with our simplification. All right, minus 1/2 times what's inside my natural log, this x cubed minus 2, becomes 1 over x cubed minus 2. And then my chain rule times 3x squared. Minus. Last one, the natural log of sine x. Same idea here. What's inside the natural log, sine x, goes in the denominator. So 1 over sine x. And then chain rule times the derivative of sine x, which is cosine x, if I can sneak that in there. All right. I'm going to clean up the right-hand side just a little bit. 1 over y dy dx would be 1 plus 6. Sine over cosine would be tangent, 6x, minus 3x squared on the top over 2 times x cubed minus 2 on the bottom, minus cosine over sine would be cotangent, x. All right, we're getting there. In order to solve for dy dx now, I just have to multiply both sides by y. But before I do that, well, actually, do this first. Let's get rid of those y's. So I do have dy dx now. And I'm going to start copying everything that's in my brackets. But remember, the original function was explicit, right? So I really don't want a y in my answer. I'd really like an explicit derivative. So I'm just going to replace that y with what y equals. Y is actually equal to e to the x cosine 6x over the square root of x cubed minus 2 times the sine of x. And that way my final answer, again, it's still a mess, but my final answer only has x's in it. And notice we've avoided multiple product rules, quotient rules. We still had some chain rules, although we avoided some of them by doing this. So the process of logarithmic differentiation can save you a lot of work in terms of all of those extra derivative rules. There's one time when logarithmic differentiation is an absolute must. Take a look at a problem like number 9 here. X plus 7 to the x power. I've got x in the base, and I've also got x in the exponent. So this isn't an exponential function, this isn't a power function, it's kind of a combination of both. Technically, these are called super exponential functions, when you've got x in both the base and the power. We don't have a rule for taking derivatives of these, so in order to do this derivative, I must use logarithmic differentiation. And it happens when there's an x in the base as well as the exponent. So let's take the natural log on both sides. The natural log of y equals the natural log of x plus 7 to the x power. And I'm going to use my log rule that says I can take the exponent and bring it down in front. So the natural log of y equals x times the natural log of x plus 7. By doing that, of course, I've eliminated my issue. I no longer have that super exponential. Unfortunately, I did create a product, so we're going to get stuck with a product rule, but at least it's something that we know how to do. So let's take derivatives. On the left side, I'd have 1 over y times dy dx for the chain rule. And on the right side, f would be x, g would be the natural log of x plus 7. So f prime is 1. G prime will be 1 over that x plus 7 times the chain rule, but the derivative of x plus 7 is just 1. And so I'll put my product rule in here. fg prime, x times 1 over x plus 7, I won't bother writing the multiplier of 1, plus gf prime, natural log x plus 7, technically times 1. So I have 1 over y dy dx equals x over x plus 7 plus the natural log of x plus 7. Okay. So I've taken all the derivatives I need. Let's go ahead and solve for dy dx, meaning I have to multiply both sides by y. Gets rid of the y's on the left side. So I just have dy dx now, which is what I want. And that's going to equal x over x plus 7 plus the natural log of x plus 7. And again, I don't really want y in my answer because the original problem was an explicit function. So let's replace the y with what y equals. X plus 7 to the x power. And there's my derivative. All right, that brings us to the end of topic J.